All right, so let's get started. Hello, everyone. Good evening. I'm very glad to open this session. This Young and the Young Machine Learning uh, for AI workshop. Okay. Hi again. I'm Dr. Meng. I'm the founder and executive director of Arcogene Technology Academy. I describe myself as a technologist, a innovation coach, and a blog writer. So it's a great pleasure to welcome all of you to this 5-day Young and Young Machine Learning for AI workshop. We are living through one of the most profound technological changes in the human history, as you are aware. AI, artificial intelligence, is already changing how we learn, work, communicate, create, and solve problems. In the future, avoid AI may not be almost as difficult as avoiding internet, smartphones, modern transportation today. So avoid learning AI is not an option. So that means learning AI is a must now. AI can greatly expand our ability, just like a machine increased human physical strength and a computer increased our ability to calculate. And artificial intelligence can help us to, do a lot of things, analyze information, write program, generate ideas, and complete tasks much more efficiently. However, note, greater productivity does not automatically create a great competitiveness. So when everyone has access to powerful AI tools, the real difference between you and others, your competitors, will come up. You use them. Successful students will not simply ask questions, ask AI to work for you. To do your work. The students should evaluate answers, make decisions, and use AI to solve meaningful problems. In the future, intelligence will increasingly become a partnership between humans and machines. Human beings must provide creativity, judgment, purpose, responsibility, and value. While AI can provide like a speed, information, analysis, and technical support. So for this reason, learning AI is no longer simply an optional interest. It's becoming an essential skills for everyone. Okay, so that's why I am especially pleased to introduce these two. I would like to introduce two distinguished instructors of this workshop, Victor and Forrest. Both are members of the United States Artificial Intelligence Olympiad National Training Camp. And also they achieve they have many outstanding achievements, including researches in if I remembered it right, biology and psychology, education, and some other areas. So their experience, what is the inspiration from their experience? Their experience represent an important direction for the future, which is we must learn two things at the same time, AI plus domains. Okay, so and previously, you probably get a major in some subjects like physics, engineering, biology. Now, again, I want to say AI plus domains will combine artificial intelligence with other fields, such as, right, medicine, biology, engineering, education, psychology, you name it, finance, and even the arts. So, and use technology to solve real world problem. Again, real world problem. Okay. So Victor and Forrest have volunteered their time during summer break to organize this completely free workshop for, middle and high school students. I appreciate their efforts because I know this not only benefit, this is not an action benefit themselves, but it's benefit everyone, our society. So that is important. Okay, solving this is associated with their research, the purpose of research, and their contribution, you know, to solve real will be benefit others, not just construct some toy for yourself. Yeah, I also want to welcome and congratulate everyone in this workshop to attending the workshop. By joining the workshop, you have chosen to invest your summer evenings in learning and challenging yourself. You're not only simply attending several classes, you're opening a door to new opportunities and take an important step towards the future. So thank you again, Victor and Forrest, for your leadership and your services. Thank you for the, for your parents and some volunteers and all these supporting organizations. I want to appreciate you guys to make this happen. More importantly, thank you every student for accepting this challenge and taking an important step towards the future. So without further ado, I'll hand over the time to Victor and Forrest. Please give them a thumb up in the chat.
Okay, thank you everyone. And thank you, Dr. Meng, for giving such a great introduction. Okay, I will share my screen now. And if you have any questions, please feel free to unmute. And if you do not want to unmute, you can also ask in the chat where I will respond. Yeah. Okay, so I will leave these slides up during the break so that like if you have not joined the Slack or if you have not created a Google Colab account, we can talk about that in the break. I'll leave this up. Okay. So everybody, you can open the notes, and I think I've sent everyone the notes in Slack and through email. Okay. And if you want to just take notes on a separate piece of paper, that's fine, or you can write on the PDF, that's also fine. Okay, we can get started. So for machine learning, machine learning is a very broad topic. Inside there's deep learning, but we're going to talk about traditional machine learning for this workshop. And there will be 3 types. The first is supervised learning, the second is unsupervised learning, and the last is semi-supervised learning. So let's look at supervised first. So in supervised, we have 2 phases. It's called training and inference, or like prediction. So for training, we have our data right here, X. What we want to do is we want to learn a function, we want to learn a mapping to get a prediction of the Y. So let's say like X is here and Y. We want to learn a mapping, a function. And the function is parameterized by theta. And we'll talk about what the theta exactly is. We'll show an example because later we'll look at linear regression. So what do we do during training? Well, there are many functions and there are many possible parameter values, right? So we want to find the best parameter value that minimizes a loss function between our prediction and the real Y, or the real value, like the ground truth value. So here we have this word, do not be scared by the notation, is argmin. It is like the argument min. So basically, we want to find the theta in a set, and this is like the set of all possible thetas. And that's usually just all real numbers. So we want to find the theta that minimizes this loss function. So that's why it's the argument, because right now it is an argument, it's a parameter. If I just said min, then that would be what is the minimum loss. So I just want to kind of differentiate that. Okay. So now, what happens after we find the best theta? Then we'll do inference. Inference, we try to predict on a test set, on this test that we've never seen before. So we've never seen this X test before. We directly predict, and you can see we're using the learned best parameter here, and we try to predict the Y test. So that is supervised learning. That's the most common form and the most like typical form of machine learning. So right here, F is parameterized by learnable theta, and F is a predetermined model. So for example, there are many models like linear regression, logistic regression, which we'll talk about today, neural network, trees, etc., transformer. So F can be any function, and F will have many parameters. And F is also modulated by non-learnable preset hyperparameters. And we'll talk about that more in the second class, like how we tune hyperparameters, etc. So hyperparameters might be like the learning rate. We'll have a set learning rate when we try to find the best parameter theta. So the learning rate will not change. But after we find the best theta, if we think, oh, let's try another learning rate and see if we can get a better model, so that would be called hyperparameter tuning. Okay, now let's continue. So now let's look at unsupervised learning. So unsupervised learning is we do not have, we may not have the Y train right here, but we actually may have it. I'll talk about what we can do if we have it. So for the training phase, what are we going to predict? We're going to predict the X. So an example is like image generation. We have an image. We try to duplicate, we try to replicate another image, and we try to make these two images very similar. So that is exactly what unsupervised learning is. You can see it's the same thing. We still have our model, it's still parameterized by theta, and we still try to find the best parameters. And the theta can be in any of the big set theta. And we try to find the best argument, best parameter theta that minimizes a loss function. And now you can see it's between X string and our predicted X. And during inference, it's the same thing. We will use our best model right here to replicate the X on a test set that we've never seen before. Okay, so now let's talk about a few examples of what this may look like. So first, clustering methods. For example, k-means. So let's say the data looks like this. There are many, there's a cluster right here, and there's a cluster right here. Well, these are all X. These are like this may be a feature and this may be another feature. There is no Y in here. There's no ground truth value in here. So, and do you need a ground truth value to find that there are two clusters in this graph right now? No. So that is k-means. But if we have the ground truth Y, what can we do? Well, we can say that, oh, I noticed that most of these are, let's say, people who have a disease. So yes, disease. And these most have the label of no. So then can I turn this unsupervised learning into supervised? Or like, can I turn it into supervised inference? Yes, you can say, oh, I have a new point. It is right here. Right here. This new point right here. This blue point. Well, it is close to the yes cluster, so I'm going to predict that this person has the disease. So that is how we use clustering. Next, we have dimensionality reduction, and some famous examples are PCA and UMAP. And we'll talk about more about that in the third class. So I'm not gonna, because right now we're kind of, the introduction took a little bit long. Okay, and then next is the image generation, like I said. So let me draw us a better graph, a better figure for the image generation. So for image generation, let me just switch over, okay, to here. So for image generation, we may have an image like this, and then we down project it to a latent vector, like a latent representation. And then we will up project it back into our predicted image. So this is what most image generation looks like. So this is down project. And this is up project. and this is our latent vector. And this basically contains information on what does this image look like. For example, if this image is like a person, then the latent vector might have, for example, what's the hair color? What is the facial expression? And it has different values. Okay, but we'll talk about more ML models uh, in the third class. Okay, and finally, let's look at semi-supervised learning, which is a small amount, a small number of samples have labels, but the majority or the rest do not. And you may ask, well, how did that happen? Well, maybe there are too many data and it's just too hard to label them all. Like for example, if you like look into astronomy, there might be like huge amount of data, but it's too hard to manually label them all. So what can we do? Well, first, there are some existing methods. First, we can have a distance equal similarity method. So that's very similar to the k-means algorithm right here. So it's the same thing. Like if a point right here, like this purple point, is close to the second cluster, then I'm gonna predict that this point is null. So that's the same thing. And pseudo labeling, we'll talk about that more in the third class, but pseudo labeling is basically like this. So right now we have our label data and we have our unlabeled data. Let's say it's looking like this. And the label data, let's make it red, and the unlabeled data, let's make it blue. Okay, so then what pseudo labeling does is we train on the red part first, because that's the part that actually has the label. Then we predict on the blue part. For the blue part, if the prediction is very confident, for example, we can define a score and a threshold. If the prediction confidence is more than 0.9, let's say, then we will put that into our training set and expand our training set like that. So that we can have more training samples. And then we retrain and then repredict and then do this iteratively. So that in the end, we may get a lot. Most of this is actually being trained on. So that is really good. Okay. Now let's move on to the topic of regression. So what is regression? Regression is we're going to talk about this is all supervised learning, by the way. Okay. Regression, the y, the ground truth, the thing that we're trying to predict is continuous. So for example, income, like $2.99999. Height, or like for example, 1.3456 meters. Temperature. So all of these can have infinite decimals. It is continuous. It is not categorical. Okay. Now, here is the training. So let's represent the training data set like this. So I will explain about matrix vector and matrix multiplication later. It is very intuitive, but right now I'm just going to represent the training data set as we have X and we have Y. That's it. So, and this notation means we have many samples. We have n samples. So basically, for each sample, we have X and Y. And I'm stacking this from n equals 0 to n, big N minus 1. There's no question, right? Okay. Now, let's look at a few loss functions. Like up here, we have said we have to have a loss function to determine what theta is the best. So what are some common loss functions for regression? Well, the first one is MSE, mean squared error. It is right here. So let's look at this formula. First, this is saying we take in the real ground truth training Y and our predicted Y on the train set. So we take them in. And what do we output? We output a scalar, a number that is more than 0, more than or equal to 0. And what is the formula? The formula is simply each y minus our predicted y, and then squared. And then we sum all of that, and then we take the mean just by dividing by n. That's it. So, and why is this good? Because the squared right here that makes sure that if the ground truth, like this subtraction might be negative or it might be positive, but our error should always be positive. Like if you are more than the ground truth or you're less than the ground truth, that should count the same. So that's why we do a squared, because we all know that squaring makes everything positive, right? Okay. And now here is a notation in vector form. And let me just say what that is. So here we can put all of these ny's into a vector, right? We can put them as y0, y1, and then yn minus 1. And then we can also have a separate, the same thing, but we have the our prediction. So I'm not gonna write it all. Okay. So what is this? What does this notation mean? This basically means we just minus these two vectors, and we all know that when we minus vectors, it is element-wise, right? So we minus them, so it'll be this minus this minus this, and then this notation is called the L2 norm. What that does is the same thing that this does. It is just we will take the square and then sum them all, and then we divide by n right here. Okay, and you can see that because we're taking the sum, the end product is just a number that's greater or equal to 0. So that is the mean squared error. And makes sense, right? Error cannot be less than 0. That does not really make sense. Okay, and some things about this is that MSE is smooth and it will provide decreasing gradients. And we'll talk about that later, very soon. And it is, however, it is sensitive to outliers. Okay, let's move on. The next is MAE, is mean absolute error. And you can see it's very similar. All we're doing is just, we want to get the absolute value. So that's like very similar to the square, right? We just want everything to be positive. But there are many ways for things to be positive. For example, this absolute value function or the squared function. So that's just a different just a different type of error, and we call that mean absolute error. Okay. So in the vector notation, these two bars with the subscript 1 is the L1 norm. And that does the exact same thing as this. Okay. So finally, of course, it is also greater or equal to 0. And we'll talk about the gradient later. So for MAE, the gradient has constant magnitude because we all know the absolute value function is like this, right? So if you have learned AP calculus, you know that this is just a line. So the gradient has constant magnitude. So it does not smoothly approach 0 near the optimum. And that's why MAE is not usually used as the loss function. However, it is definitely less sensitive to outliers. Okay, now let's move on to linear regression. So here I'll talk about a lot of the vector notation, like for the above. If you did not fully understand, that's fine. I'll talk about the vector notation very in detail now. Okay, so first, let's say we want to predict a house's market value based on the land area, the distance to the nearest school, and the average neighborhood annual income. So you can see that the market value, that is a continuous variable, right? The land area is a continuous variable, the distance is a continuous variable, and the average neighborhood is a continuous, the income is a continuous variable. So the x and the y are both continuous. They're both just scalars. They're both just numbers. Okay, and you can see that each sample can have many features, right? So in this case, we have 3 features: the area, the distance, and the income. So let's define a feature vector. Let's find a training sample feature vector right here. And vectors and matrices, they're just ways of storing information. They're not anything that is super complicated. So you can see that right here, I'm just storing. So the superscript n means we're looking at one sample. So for each sample, I have d features. That's it. So this might be land area, this might be distance, and this might be income. That's it. So that is the x vector, and that is with a superscript, and that means that for the nth sample. So, and this notation right here is saying that this is a vector with dimension d. That's it. And each individual value is a real number. So that is very easy, right? Okay. So I'm basically, so what I'm doing is I'm just storing the values in the vector. That's all I'm doing. Okay. Now let's continue. So that was a vector for each sample. Can we combine that into a big feature matrix? Yes. So the big feature matrix is a big X. And the transpose right here. So a vector is always like this. It has many values. So the shape is D by 1. So there are D rows and just one column. And the transpose means we're going to just turn it around. That's it. That's all the transpose means. So what I'm doing here is I'm turning each X horizontally. I'm laying it flat. And then I'm going to stack them all like this into a big X vector. So what that basically is, so this big matrix will have n rows, and each row is a different sample. And each column is a different feature. So this will be x0, 0, x1, 0, x2, 0. And then this next row will have x0 down here, but it is the first sample now. I mean, it is a sample of index 1. And then x1, 1. And then x2, 1. So that is all we're saying. We're just storing all information in a big matrix. That is it. And what does this mean? This means that we have, oh, okay, let me increase the screen. This means that we have n rows and d columns, and every value is a real number. It's a scalar. Okay. Now let's move on. So what is the linear regression model? The linear regression model is simply a linear combination of features, or you can say it's a weighted sum. So we're going to predict each sample's y with a bias term and these individual weights. So the theta 1, theta 2, theta d, those are all weights, and they're all learnable. So basically learnable means what should those theta be? What should those thetas be? And above, I've talked about that for supervised learning, we're trying to find the best thetas, right? So this is what I mean by like linear combination and supervised learning. Okay, so basically we just look at each x, each feature gets its own weight. We have a sum and we have a bias and we predict the y. That's it. Now, notice, what can I do? Can I say this theta 0, can I expand that to theta 0 times 1, right? I can expand that. So then let me define, so first let me define the theta vector right here. I'm just putting the d scalars into a vector. That's all I'm doing. I'm just storing them in a vector. And you can see that it is d plus 1 because we have the bias right here. And then these are for the d features. So that's why it's d plus 1. So right here, you can see that all I'm doing is timesing by 1, and I can always do that, right? So what if I added a 1 to every vector? Every of our training vectors, and let me call that to be x bar. Let me rename the vector to be x bar. So I've just added a 1 here. And now, of course, the shape is now d plus 1. Okay? And I'll talk about why we do that. Next, because we did this, our big feature matrix, our big training feature matrix will change as well. So it is the same, we stack them all, but because we've added the 1, can I say the ones are all right here? There's a 1, there's a 1, there's a 1, and there's a 1, right? So above, like this big matrix, what we did is we just added a 1, 1, 1, 1. So now the shape is n by d plus 1, right? And what we did is we just appended a column of 1s to the left of x, right? Just like what I said right here. Okay. Now let's continue to look at, so now we've did all of the x and the theta. Can we put the y's in the vector as well? Yes, let's do that. So this is just the 0th sample, the y, the first sample, the y, and the n minus 1th sample, the y. So the shape is n. So we're also just, this is just storing everything in a vector. There's no complex math yet. Okay. So finally, can we use this vector notation to write this linear combination equation right here? So now I need to introduce to you matrix multiplication. If you have any questions, you should ask in the chat. Or you can unmute. Okay, let's get started. So now let's talk about validation. So far we know that we need to have a training and a test set. And we know that training an ML model means finding the best parameters, like the theta star, right? Given a specific set of hyperparameters, and hyperparameters are not changed. However, we should also be able to tune hyperparameters, right? For example, yesterday we learned linear regression. In linear regression, we know that a hyperparameter is the learning rate. This alpha right here. So we should be able to change this alpha. Maybe the step size is too big, or maybe the step size is too small, right? So how do we do that? Can we use the test set to tune these? Actually, it might make sense at first, but no, you cannot do that because of data leakage. And what kind of data leakage is that? It is when we tune hyperparameters, we are saying which learning rate is the best. So for the specific test set samples, if we just tailor the learning rate to those test samples, then that is basically like cheating. The test set should be a final non-biased evaluation. We cannot look at it anyhow before. So yeah, right here, if we tune hyperparameters, we're literally cheating. We're seeing which hyperparameters are the best. It's kind of like with parameters as well. So maybe on a test set, one learning rate is super good, but we cannot know that beforehand. Otherwise, we would be cheating. Okay, so here's a little summary. For the training set, it is strictly for optimization. It is strictly for optimizing our parameters to learn the internal parameters. For the test set, it is strictly used at the very end to just evaluate on unseen data. So we need to create a validation set to tune hyperparameters. So let me write right here what it typically looks like. So typically, like let's say this is all of our data. Typically, we have 15% is validation, 15% is test set, and 70% is train set. So that is what we usually do. So that is if, and this splitting is if, for example, a competition like our competition or a problem gives you full data and you need to split it yourself. But if a problem just gives you the validation set, then just use it. If a problem just gives you the training and the test set, then it is your job to create your own validation set to see if your model's good. And a lot of the times, a problem will not tell you your performance on the test set. So you have to use the validation set to know how good your model is. Okay. When we do training, we use a loss function like MSE for regression and cross entropy for classification like we talked about yesterday. And we choose a loss function that is differentiable and stable for gradient descent. However, that is not how we should tune our hyperparameters. Because if I just say, oh, the BCE loss of a logistic regression model is 0.1, that does not make any sense. But when I say the accuracy of a logistic regression model is 0.9, then I know that's very good. So the validation set, we tune hyperparameters using an evaluation metric. And we also talked about all of those yesterday, like MSE for regression. MSE is both the loss function and evaluation metric. But for classification, we use accuracy, precision recall, F1 score. So now let's talk about a few algorithms for hyperparameter tuning. The first is called grid search. So grid search is we define a manual list of specific values for each hyperparameter. And we might have many. For example, learning rate is a hyperparameter, and the regularization term that we learned up here, that's also a hyperparameter. So for example, I'm going to say, oh, let's try learning rate is 0.01 and 0.1, and let's try regularization strength of 1 and 10. So for grid search, we're basically building a big grid of possible values. So for example, like the learning rate is 0.01 and 0.1, and the regularization strength is 1 or 10, then we need to try all of these points. So that's basically a grid. We need to try every single possible combination. So the pros of that is that it is very deterministic, it's very thorough. It basically guarantees that we will find the best combination. However, it is very inefficient. And if we have already many hyperparameters and we just add one more, then there'll be a whole bunch more combinations. So that just is huge, massive computational power. That's not good. Okay, the second option is called random search. Random search is we define a statistical distribution or range for each hyperparameter. Like learning rate, we're going to sample it uniformly from 0.001 to 0.1. And we randomly select combinations from these distributions for a fixed number of total iterations. So because of this fixed number of total iterations, we can keep our search to, say, just 50 iterations. But in grid search, we have to do all iterations, so that is kind of bad. So basically for random search, we have like, for example, the learning rate is 0.01 to 0.1. We just pick a random value. And then the regularization strength is 1 to 10. We pick a random value. And we do this for 50 times, let's say. So the pros of this is that it is much more efficient than grid search, especially when some hyperparameters matter significantly more, because we do not waste time repeating identical values of one hyperparameter to just change another, right? That's what grid search is doing. But the cons of this is that it is non-deterministic and it's kind of based on luck. We do not learn from past mistakes or successes. So, but already, random search should be better than grid search. So for ML problems, if you have many hyperparameters and you want to try very many values, random search should be better. The last type of search is called Bayesian search, and it is a little bit too complicated for us to talk about in our workshop here. But basically, it's a smart algorithm that learns from previous hyperparameter combinations by building a probabilistic model of the relationship between hyperparameters and the validation performance. So it basically learns which decisions are bad and then what I should do next. So, of course, it's better than both grid and random search, but that is a little bit too complicated. And in coding, you have to import special libraries for that as well. So it's not very easy to use. Finally, let's talk about k-fold cross-validation. So here, my 70-15-15 example. What if the 15% split, what if that was not very good? What if that split did not really represent the whole data set very well? What if it just happened to contain a lot of one class and very few of the other? So what should we do? Well, we can use something called k-fold cross-validation. So here is what it does. Here's the algorithm right here. So first, we should shuffle the whole data once at the start. So let's say this is the whole data. We're going to shuffle it, so it's all random. And then we split it into k equals sections, and usually k equals 5. Usually. So, okay. Then what we will do is just we say this is used for validation and this is used for training. And then we repeat. We say now this one is used for validation and the rest are for training. And then this one's used for validation and then the rest are for training. So we just iterate this through this 5 times. So we'll get 5 validation scores, right? In the end, we just average the k evaluation metrics, and that provides a better like validation score to for a whole data set. Because maybe in this 15 split, it was kind of bad, right? So we use this average now to select the best type of parameters using whatever search, like random search. And that's also good because, for example, you can see here, this training data set, you might worry that, oh, these 15% might be very valuable data. I also want to train on that. Well, in this k-fold cross-validation, you can see that we basically train on all data as a whole, and then as a whole performance, we have a validation score. So cross-validation is very good. Okay, now let's move on to, in general, how should we solve open machine learning problems, which is very related to our competition. Is we have a data set, and let's say it's classification. We want to have a high F1 score. What should we do? So this is very important, and you should always keep these 7 points in mind. This is what most ML engineers do as well. So first, we should have exploratory analysis. First, you should check missing data. So let me go to another whiteboard to kind of talk about very quickly how we should, like if we have missing data, what should we do? So first, we can delete. That is a method. If we delete, we can delete whole rows or whole columns. For whole rows, that's usually what we do, which means that this whole sample, we do not want it. So, but the downside of that is just it wastes usable data in other columns. For columns, if we decide to drop a column, then that might be, this column contains so many missing values that like it does not even provide useful information. So that's when we drop a feature. Columns are features, right? Okay, so that is the first method, is we can just delete. And that, if you have very few missing values, then you should delete. However, there's another method, is we should impute the values. So let's talk about what should we do for numerical values, features. We have 4 different things, methods. First, we can just replace their missing value with the mean or the median. And the mean is usually good if the feature is normally distributed. And you also learn that in AP statistics, the mean is very representative if the distribution is normal. But for median, it's very good if the distribution is skewed or there are many outliers. So that is just replace all missing values with the mean and the median. And the mean and median is just one number. So is replace all the values with just one number. The second method is just fill it with 0 or some random number like -999. So that might be good because the missing value might actually provide some information. It might be like for example, in the hospital, we did not collect this feature. The feature is missing because this patient is healthy. Like, we did not collect a specific medical feature because this patient is already healthy. This patient should not be in the ICU, for example. He should go out now. So sometimes missing does not just, it actually provides a lot of information. So just fill it with a random thing, that should represent it well. The third method is find like the k most similar rows based on other features, and then we just average their values. So that is also quite good. So that is saying find the k most similar, like other samples in the data set. So they will not have, for example, this feature, let's say land area. They will not have land area be missing. So what do? We just average their land areas, and that's my land area. So basically, we just find k similar samples. And how do we find similar? Well, you can do many definitions. For example, the values are close or whatever. So just find the k similar samples. What is their land area? And if my land area is missing, then just I'm gonna be their mean land area. So that's very good. And the last is called forward filling. Forward filling is usually used for time series. So like if the temperature over a day is 23 degrees, 24 degrees, missing 26 degrees, then we're going to fill it with 24 degrees, not 25 degrees. Forward filling is just what is the previous, just fill it. There's also other methods like interpolation that would fill it with 25 degrees, but that is a little bit more complicated. Okay, and then for categorical variables, let's look at what we're going to do with them. So there are just basically two methods. The first is replace all missing with the mode, the most frequent. So example, for colors, the most frequent, let's say is green. Okay, then just replace all missing values with green. But that might lead to some bias, right? Okay, the second method is to replace it with another new category called unknown or like missing. That's the same thing with this one, right? The unknown feature, that like the fact that it's missing might be very helpful. Just like what I said, the medical example. The fact that it's missing might be very important. So if we replace it with unknown, that will tell the model, oh, this is a separate category. All right. So one final thing about imputing features is we should always split into train, validation, and test, and then impute. So because we do not want data leakage. So after we split into train, validation, test, let's say we want to impute numerical features. We calculate the mean in the train set, and then use that mean to impute numerical variables in validation and the test set. We cannot, just like we talked about previously for the standard scalar, for the z-score normalization, we have to use the train mean. We even have to use the train mean on the test set. So that is very important. So for imputing, remember that we need to split first and then impute and only use the train statistics. That's a very important part of machine learning. Okay, next, let's check whether data is balanced or unbalanced. And we talked about a lot about that yesterday, like the accuracy and F1 score. So for that, there are kind of two methods to counter that. First, we can do something called stratified sampling, and that is just we try to make sure that when we split into validation and test, we try to always have some samples in the low represented group. For example, 95% of people have a disease, but 5% don't. Then we always try to get some of that 5%. That's stratified sampling. And another method is just using weights on the loss. So for example, if this patient, only 5% of people have this disease, then whenever I calculate the loss for such a sample, I give a higher weight so that it counts more. And if the model makes a mistake, it penalizes the model more. Okay. The next is you should always understand the data type, like numerical or categorical or a mix in the data. And you should always know the data range and the orders of magnitude. And that's very important. For example, like we said before, you should always standardize data. If one feature is in the 0.01 range, but another feature is 10,000, for example, income, salary, then we have to standardize features, right? Okay. Next, you can also generate plots to visualize data. For example, time series over time. That's very good. So you get to know what the data looks like. The next step is data preprocessing. Data preprocessing, first, like I said, normalization. The second, one-hot coding, like we discussed. Finally, create your own validation set if none is provided, and you can choose whether to perform k-fold cross-validation. Next, basic or no feature engineering. So when you just start out with a machine learning model, we do very basic or no feature engineering. And feature engineering, but it is very important. So we provide, for example, very light feature engineering. So for models that are linear in nature, like what we talked about yesterday, and support vector machine, we'll talk a little bit about that next time. Feature engineering is needed to create nonlinear features. So like I said, squaring and product of two features. But when I say light feature engineering, I'm not saying, for example, we have 100 features. We want to do the product of every combination. That may be too much. But if you have some kind of, for example, if this is a problem is in biology, you know that these two features, when they multiply, that is like intuitive. Then you should just add that product of those two features. We don't need to add more. Okay. Finally, dimensionality reduction. We'll talk more about that next time as well. But I will talk a little bit about that right here. So for dimensionality reduction, we have two methods. The first is feature selection. So that is just select the best features. There are 100 features, but that's a little bit too much. I want maybe only 5 features or maybe 10 features. So how do we do that? Well, the first is we can remove very highly correlated features because like we previously said, multicollinearity, want to avoid that. And the second one is we want to delete features that don't really change much. So this feature doesn't even change much if I have the disease or I don't have the disease. Then is it likely to be even useful? No. So that is the second, is features that don't change much. Okay, so that's feature selection. The second is feature extraction. So for feature extraction, there are two methods. The most common is called PCA, Principal Component Analysis, and UMAP. So let's just talk about PCA very quick. So PCA is, let's say here is a feature X1, here's a feature X2, and maybe they look like this. But I just want to reduce that to one feature. What should I do? So let's say we have a line here. What I'll do is project this feature onto this line. Project, project. So you can see that I can represent all features using a line, right? So my line, it will become this point. It will become this point. So now I've effectively reduced two features into one feature. But what line is good? Well, that is what the PCA algorithm finds. It tries to have the maximum variance. For example, if I have a line like this, look at what happens. This point goes to here. This point goes to here. They're like the same point on this line. So that's very bad. How do we differentiate what is happening? So we want to try to keep the variance of all the features, but we also want to try to reduce features. Okay, so that's what PCA is. And PCA, first, we can prevent overfitting. That's very nice because we're trying to reduce the number of features. The second is we can speed up training because we'll go from, say, 100 features to just 5. And the last is visualization in 2-dimensional space and 3-dimensional space. So sometimes when we have 100 features, we cannot really visualize that like this. So we should use PCA to get it into 2 features, and then we can visualize it on a grid. And if they form clusters, oh, then the problem can be easily solved, right? Okay. So that's dimensionality reduction. And finally, we will use our machine learning model. So we should try machine learning models based on intuition. For example, I feel like this problem should be solved with linear models or kernel-based methods. We'll talk about all of that tomorrow, or tree-based clustering, etc. After you try machine learning models, you definitely should try other ones because we do not know which ones are the best. And then after that, you should perform more feature engineering and iteratively scale up and improve your F1 score or MSE. Okay, so finally, let's talk about so that is it for other machine learning methods. And for the last maybe 20 or 10 minutes of class, I want to show yesterday we talked about linear regression, right? So I want to show code of how to code linear regression from scratch. And we do not need this for the competition as well. So I'm just trying to show you how we code linear regression. So you do not need to fully understand the code if you do not know how to code in Python or you do not know how to code in NumPy. That's fine. I'm just wanting to show you linear regression in code. So here's the formula that we derived last time. We need to use these formulas now. That's how we update the parameters, right? Okay. So here is the Colab. And so the code is also here. So this is just PDF that also shows the code. Okay. So first, here is our function, linear regression. And it takes in X train, Y train, number of epochs like we discussed last time, just 100 epochs, and the learning rate. The learning rate, let's set it to be 1e negative 3 is just 0.001, just 1 times 10 to the negative 3. Okay, so here is our SGD algorithm. And last time we learned about stochastic gradient descent, which is we update using only one sample every time in each epoch. So here, we're going to initialize all coefficients with just 0. So let's initialize all coefficients with 0. And then this is just to keep track of the loss over time. And I'll show you the graphs later. So first, we shuffle. Because in stochastic gradient descent, if we don't shuffle, then it's always the first one will the first sample will affect it in some way, and the second sample will affect it in some way, and the third sample, we should shuffle it to be more representative. So you can see here what we're doing. Theta equals theta minus learning rate times here is basically here, right? We're replicating the y minus the real ground truth y times the x. That's the formula. If you don't really understand this code notation, that's fine. But I'm just showing you that it is doing exactly what we derived last time. Okay, and I'm just keeping track of the loss here. Okay. And then here I will be plotting the loss and you'll see below. Now, in the predict function, what do we do? Well, all we need to do is this. X test multiplied by self.coefficient, which is just the theta. Oh, which is just the theta. And that equation is also right here. Okay. So that is on the test set. That is prediction on the test set. Okay, finally, the score function is just to calculate the MSE. MSE, look, it is y prediction minus y test, have the power of 2, and then mean it. That's it. Okay, now let's define the data set. So our data set, we're going to have 2 features, including the bias. So it's basically just one feature, but we want to also have the bias. Let's say we have 200 training samples and 20 test samples. Here I'm just randomly generating ground truth theta, and it's theta star. And we want to try to learn this theta. So you can see here the ground truth value. It's right here. So let's also generate some X train. So X train is just the feature. So let's say it has a mean of 5 and a standard deviation of 2. That's it. And you can see the size is n trained by d minus 1. And that is exactly what we derived last time, right? The data. Okay, so right now, because I have 2 features including the bias, so the X train is actually just many rows, 200 rows by 1. That's it. And it just has like a number, maybe like 1.1, 2 point, whatever. And the mean is 5, standard deviation is 2. Let's compute the Y train. Well, let's use our ground truth values. Here's the ground truth bias, plus the ground truth weight times X train. That is exactly the ground truth Y. let's add some noise right here so that it is non-perfect, like real-world data. Let's do the same thing for x-test and y-test. So here's the ground truth y-test. So that's what we want to predict later. Okay. So now let us plot the x train and the y train and the x-test and the y-test. You can see here. Here's the x and here's the y. And I purposely chose only one feature so that I can plot it in the 2D plot like this. So you can see that the blue points are the train points and the red points are the test points. And it forms roughly a line, but because I added the noise, it's not perfect. And that's what we want to try to get this line. All right. So next, here is z-score normalization. We defined it above. What do we do? Get the mean, get the standard deviation for each feature, for each column. And then all we need to do is subtract it, divide, subtract it, divide. That's it. And you can see right here, the mean is x. We do it on x train. The standard deviation, we calculate it on x train. And then we subtract, on the test that we subtract this exact same mean and divide by the exact same standard deviation. So right here is what I talked about. We do not want data leakage. We do everything on the x string, and then we even use the x string mean on the x test for normalization. All right. Next, let's define a function called add bias. That's just what we derived last time. Append a column of ones to the feature matrix. So before I said it's 200 by 1, so now it's 200 by 2, and here is all 1, and here's the features with a mean of 5 and standard deviation of 2. So that's also what we derived last time. So these two lines basically do that. All right, finally, we're going to fit the model. So I want to demonstrate to you what happens when we do not do normalization. So I will show that very soon. So here I'm saying if we use z-score, if we do the normalization, then we do it. And then we update the x-train and x-test. And then here's our model. We fit it using the x-string and the updated x-string and the ground truth y-train with these specific parameters, hyperparameters. These are hyperparameters. And then we predict, model.predict. Finally, we look at the performance and we return the performance. So now here, you can see the performance. The MSE is 0.3. It's pretty good. And here is the training loss curve. You can see the training loss is going down. It's very accurate. Oh, okay. The training loss is going down like this. So you can see that over all of the epochs, the gradient descent is working. The loss is decreasing. And here's just the norm of the coefficients, just to show you that we started from 0, right? I said we initialized with 0. But gradually, we actually came to a stable value. We converged. So that's what the norm of coefficients is saying. Okay. Next, here is generate plots. So here, I just want to show you, we have the x-test and the ground truth y-test. But I want to plot our predictions on it. So we have the y prediction and the x-test. I want to show you what our linear regression line is. Then I want to show you the residuals. The residual is y-test minus y-preds. I want to show you what that looks like. So that looks like this. So here is our test set. You can see that here are all of the test points, and here is our predicted line, linear regression line. It's very accurate, right? Very good. And here's the residual plot. The residual plot, you can see it's all kind of random. And if you learn AP statistics, you also know that random residual is good. So some points, if they're above the line, like let's just look at, so if some points they're above the line, then the residual is, if like the test point's above the line, then the residual is positive because it's y-test minus y-pred. If the test point is below the line, then the residual is negative. So you can see here. And they're all centered around 0, which is good because we want it to be very close the y-test and the y-pret to be close. All right. Now, what happens if we do not use z-score normalization? Right here. I purposely turn it off. You can see that the loss is now super wonky. And it does not, and it just goes up and down, up and down, up and down. So what is that doing? Well, does that look like this case? It looks very similar to this case, right? We're just bouncing around the center, but we're not really reaching the center. And also like this case. Oh, also like this case, where we might be just bouncing around the corner, but we're not really actually reaching the end. Why? Because the learning rate might be too high. And why is it in this case, when I do not normalize it, the learning rate just becomes so high? Well, let's go back to our equation right here, our update equation. Update equation here, I'm multiplying by x train. And I initially said my x train, the data set right here, the mean is 5. So the values are actually pretty big. The values are like 5.0, 5.1, 5.2, 4.8. The values are pretty big. But when I scale it, when I do z-score normalization, we said the mean will go to 0. So then the x train values will be 0.1, 0.5, negative 0.2. So here, when I do not normalize it, and I multiply by the x train, this term will become very, very huge. So that my learning rate seems like I'm doing a very big step. So I must decrease the learning rate. When I do not, when I do normalize it, the x string is quite small and the learning rate is very optimal for it. So hopefully you understand why this happens. And you can also see here, this plot. It is not really converging. This plot right here. It is not really converging. It is like bouncing around. Okay. So here's the Colab notebook. I want to show you what happens when we decrease the learning rate, because I just said the learning rate for this case is a little bit too high. So now I want to show you what happens when we decrease the learning rate. You can see here. So right now I'm just going to run it all with 1 times 10 to negative 3. Okay, it just ran. You can see it's the same plots right here. But let me just turn the learning rate down. So right here, look, I'm going to make it to be 1 times 10 to negative 4. Now let's see what happens. I'm going to run all. Okay. So here is when we do use normalization. You can see here, it is more gradual. The loss function is more gradual. Why? Because the step size is smaller, right? We move very little. So the training loss is not, it will decrease very slowly. But right here, you can see when we do not use z-score normalization, it converges very nicely right here. So this is a perfect example to show you the learning rate is very important. It's a very important hyperparameter to tune. It's a very important hyperparameter to learn about as well. Okay. So I think that is it. So right here you can see I've opened the Google Colab, and Google Colabs, we have 2 things. We have a text cell and a code cell you can see up here. So you can see all of these are text cells where you can just write stuff. And there's a lot of, for example, these are all headings. There's too much to teach. So if you want to like have some fun formatting for the competition or for future uses of Google Colab, you can search how to do certain like titles and all of that. But for the text cells, there's also, for example, here you can there's some special characters for you to make the text, for example, code-like. Okay. But the most important thing for Google Colab is the code part. So you can see here, I can create a code cell. So for Google Colab, it is Python code. So it is not like Java or C++. If you've learned that before, it is Python code. So and the good thing about Colab is it has memory. So let's say we just define a equals 3, and let's just run it. You can click the left button. And then let's just print out a. And you can see it's 3. But if I now do a equals 5, I just set a equals 5, and then I run this cell again, you can see it is 5. So it has like memory. So that's usually a good thing, but also sometimes when you're doing code, sometimes you like change a lot of code and you rerun the same cell without rerunning the whole notebook. And because you changed and then you only reran your like the cell that you're on, sometimes the memory is still there and a lot of stuff is messed up. So like an example is we have like a equals 3. Let me just run it again. And then let's just say like a equals a plus 1 and then print a. So I run it once, it's 4, but I just run the same cell again and it's 5 and then 6, 7, 8. So be careful of like this feature in Google Colab. Okay. Other than that, I don't think there are also some other stuff like you can code with AI like right here. You can open Gemini and all of that. But I think that is the most important things about Colab is a short little introduction. Okay, now let's get into today's notes. Okay, so today we're going to learn an overview of all the common machine learning models. Because for the competition, we want you to know many machine learning models so that you can select the best ones for your own data set, for your own topic. And most of these are accessible from a library called sklearn, called scikit-learn. So you do not, like yesterday and the day before, we showed you gradient descent algorithm on linear regression. But sklearn has done all of that for you. It will do that in the background. So you do not need to actually do the gradient descent algorithm. You don't need to do anything like that. sklearn will just train the model for you. So all we need to do today is first learn about some models and second, learn the syntax in code of how to use sklearn so that you can just employ this model and just use it. And you can also use AI to code for you, but you should understand everything. And we'll like you can use AI to help you with the syntax, for example. But we'll go through everything today. Okay. And the other important libraries are NumPy, Matplotlib, and Pandas. If I'm not really learned that, that's fine. You can ask AI for help for the competition. But if you have learned that, then it should be pretty easy. Those are just like libraries for like NumPy arrays or Panda data frames if you have learned it before. Okay, so first, yesterday we talked a lot about polynomial preprocessing, which is just adding polynomial features on top of the existing features that we have to introduce non-linearity. Because many problems like a parabola, you cannot solve it with linear regression, right? Like we talked about yesterday. Okay. However, do not use polynomial preprocessing when some features are categorical. Because categorical, like let's just say you're multiplying two features. Well, yesterday we talked about one-hot encoding. It's just 1 and 0 and 1 and 0. When you multiply, it's usually just 0 times 1 will just be 0. So everything will be zeroed out, and that does not make any sense. And also squaring a categorical feature, that also does not really make sense. So do not do polynomial preprocessing on categorical features. And also be careful about polynomial processing when there are many features. Because like we said, for just factor, like we have a degree of 2, for example, x1 squared, x2 squared, x3 squared, but also x1, x2, x2, x3, x1, x3. All of those, the more features you have, the number of new features that you add will just increase a lot. So be careful about that. And to prevent higher order engineered features like I just talked about, use standard scalar afterwards. Okay, from dominating. Okay. So polynomial preprocessing, first of all, it is definitely not a model, right? It is just feature engineering. but it does learn what features xstring has. So you need to you need to give xstring to the polynomial features right here. You can see here in the code. You need to give xstring to that instantiated polynomial features from sklearn. It then applies the same transformation to xtest. And we talked about yesterday why we do that to prevent data leakage. So polynomial preprocessing, of course, increases model complexity to make sure, and you need to make sure to use regularization if you want to prevent overfitting, like we talked about yesterday. So here, you can see here from sklearn dot preprocessing dot is just what is in the library or what is in the model or what is of the model. So from the preprocessing like unit or like storage of sklearn, I want to import polynomial features. And in this lines, we're just instantiating uh instantiating a class polynomial right here. So we give it degree equals 3, so that is just x1 cubed, x2 cubed, x1 x2 x3, x1 squared x3, for example. And include bias, make sure to set it to false because the default is true. And if it is true, just add an all one column to xstring. And usually you do not need to do that. Like in linear regression, we talked about adding the all one column, but usually we do not need to do that. Because for like linear regression from sklearn, it will do that for you. So make sure to not let this add a all one column for you. And then all you need to do is polynomial.fit transform. Fit transform is a function under polynomial. So we fit on xstring and we transform xstring. Then we just simply transform xtest using what we learned from xstring. So fit is also the same thing as learn in a lot of sklearn syntax. All right, now let's talk about standard scalar. So for standard scalar, we talked about yesterday, it is the z-score normalization. Let me write that really quick. So standard scalar is the z-score normalization that we talked about yesterday. It is very important in both machine learning and deep learning. Across all samples, each feature's mean and standard deviation will be calculated, and then we normalize by subtracting the mean and dividing by the standard deviation. Scaling prevents features with large magnitudes from dominating the loss function in linear regression, logistic regression, a lot of other models as well. And especially for models that you need to calculate the distance, like in KNN, K-means, we'll talk about that today. So you don't want like big features with large magnitudes just dominate the distance because that feature might not actually be very important, but you're letting the fact that it has a large magnitude, has a large range dominate. So that is unfair. Okay, so for for standard scalar, all you need to do is sklearn. It's the same library under sklearn called preprocessing. And then here we instantiate a scalar. And then we do the same thing, fit transform on the x. What this will do is it'll just calculate, it'll store the mean standard deviation from x string and then normalize x string. And then when we do dot transform x test, it will use the same x string mean and standard deviation to transform the x test to prevent data leakage. Okay. Now let's talk about PCA. It is principal component analysis. Talked a little bit about it yesterday, but we can talk a little bit about it more today. So PCA reduces the dimensionality of data. So let's say the X string is n by d. We'll transform it into n by d nu, where d nu is less than or equal to d. So let's say like original data is like this. It has like 3 features. These are the columns. Then we might just want to decrease the number of features to 2. So you can see here. So dimensionality reduction is to turn 3 features into, let's say, 2 features. And keep in mind that this is not feature selection. Feature selection is just we're gonna like drop one of the features because it's kind of no use or does not contribute a lot. But PCA does not like that. PCA, like we talked about yesterday, is called feature extraction. So it is use all of these 3 to make the 2. So it's kind of like in synergy, we want to make these 2. Okay. So the mechanism by which PCA works is it will take the top it'll form these D new features by trying to maintain the most variance. And I will talk about that right now. So data must be scaled before dimensionality reduction. Keep that in mind. So, and we usually scale data using the standard scaler right here. And use PCA when you want to visualize your data in, let's say, like 2 dimensions. You might find the data to be clustered. Then you can know that, oh, the right cluster is label 1, the left cluster is label 0. My machine learning problem is done. Okay, so here is the syntax for encode for how to import PCA. So right here, we want to use the decomposition library under sklearn to import PCA. And then here we instantiate a PCA model. And here we're saying the n components is 4. So let's say maybe our original dataset had 15 features. So now we're compressing it into 4 features. So that you can set yourself. Same thing, fit transform. So it'll learn the characteristics of X-string and then transform X-string into 4 features, and then use those same characteristics to transform X-test to avoid data leakage. And finally, you can also print out the variance, like it'll have like something called explained variance ratio, and you can see like each principal component, how much variance, like what percentage of the variance is retained. But that, if you learn more about PCA, you'll understand more, but right now we don't really need to worry about it. Okay, let me draw a simple diagram of PCA like last time. So basically PCA is just, let's say we have 2 features and the points are like this. We want to find a hyperplane to project the features onto it so that we have the maximum variance. So here is the projection. Here's the projection. Here's the projection. So our new points are this one, and this one. So you can see that when we project it all onto this 1D line, we've successfully converted our 2D data into 1D data. But some problems are if we use, let's say, this hyperplane, then you can see this point goes to here, this point goes to here. They're essentially the same point. They're very close. But actually, they're not very close because in 2D space, they're like this. So you can see that, of course, we're losing information, but sometimes we have to do it to avoid overfitting, or if there's like a billion features, we want to try to decrease it to have faster training. So that is PCA. So we're just trying to find the best hyperplane to project it onto so that we retain the maximum variance. And like variance, for example, like I just said, maybe these 2 points are very close, then the variance is not very high because they're very close. And we know that like for like a data set, variance is just how far from the mean are the points. So if the points are very spread out like this, then that is high variance. That's what we want. We want to retain as much information as possible. Because when we reduce the dimension, it'll definitely erase some information. Okay, now let's go to linear regression. So for linear regression, yesterday we talked about, I showed you the code for linear regression from scratch, but we do not need to do that. We can simply import from sklearn. So of course, linear regression is the simplest of ML models, and through gradient descent, it minimizes loss function and achieves a line of best fit. It is we're trying to minimize the sum of squared residuals, right? That's the MSE loss. And we use linear regression when the output is continuous. So the common evaluation metrics, of course, are mean squared error and something called R squared score. That when you go to AP statistics, you'll also learn more about that. We don't have to dive deep into that. So MSE measures the mean of the square differences, yeah, between the true value and the predicted value. So of course, the lower the better because it's mean squared error, so the lower the better. And R squared, it measures how much of the variation in the y-test can be explained by the model. So for R squared, the higher the better. And it ranges from 0 to 1, with 1 being perfect. Okay. So for MSE and R squared, just keep in mind that R squared is basically only designed for linear regression, but MSE is very important. MSE is used all over deep learning, all over machine learning. So yeah. Okay. Next, the risk of overfitting is very low, of course, because linear regression is a very simple model. But for high-dimensional data, we can always use regularization for preventing the model to learn the data as random noise. And below we'll show ridge regression and lasso regression like we talked about yesterday, how to import them from sklearn. Also, you can also remove highly correlated features like what we talked about yesterday. So for linear regression, it is the library name is called linear model in sklearn, and we just import the model right here, instantiate the model right here, and the default parameters are all good, so you don't need to like specify anything here. Then just simply fit it. Fit it just means find the optimal parameters. And then we do model.predict on the test set. And we'll get the ypred right here. For evaluation, sklearn also has it for you. You do not need to do any formulas. So it's under the metrics library. So just import MSE, R-squared score, etc. And then all you need to do is give it the ytest ypred, and it'll calculate it for you, ytest ypred. Finally, you can look at the weights and the biases of the model after you've trained it. So of course you have to run this after you have run this cell, right? After you have trained the model. After you train the model's coefficients, that's the weights, that's the thetas, you can print them out. And also the intercept is the bias, which is theta of 0. So that you can also print it out. All right, now let's talk about ridge regression. So ridge regression, like we talked about yesterday, is just linear regression, but L2 normalization. So we add this term right here. And remember that this is I from 1 to D, so we're not regularizing the bias. Remember to never regularize the bias. Okay. So we use this for high-dimensional data as there will be many weights and it is easy to overfit. So this just tries to make the weights be closer to 0, and when you're closer to 0, it means that each feature does not matter much. It means that we're basically not even worrying about the features. So that's why it is regularization. It's like regularizing the model. Okay, so this very simple is the exact same syntax. So again, in linear model, import just ridge, instantiate the model right here, and here is the alpha parameter right here is basically this lambda parameter right here. So if you have 1, that means it's just regularization. But if your alpha is 0, then that means no regularization. Okay. And then same thing. Fit on the X train and Y train, predict on the X test, and that's it. And evaluation and interpretation are the same as linear regression up here. All right, let's go to lasso regression. So for lasso regression, we talked about yesterday, that is linear regression with L1 normalization, and the formula is like this. So L2 normalization is the squared theta. L1 normalization, it is absolute value. So remember that as opposed to ridge regression, lasso is better at making some features completely and exactly 0. So that's very effective for like feature selection. That kind of models feature selection, right? We're just completely ignoring. But for L2 normalization, like last time in the notes, I said it's a little bit more circular. Uh, if we want to prove why it is completely 0, there is a simple geometric like way of thinking, but that is a little bit too complicated for our class. So just remember that ridge regression is a little bit more circular. It's not as like diagonal as lasso regression, and lasso regression makes features completely 0. So it's a little bit more harsh. Okay, and then the syntax is the exact same thing, but just we have lasso here, and when we instantiate, we use lasso, and then everything's the same. Okay. Now let's talk about logistic regression. Logistic regression, like we'd said in the first class, just linear regression, but we have a sigmoid function because logistic regression is for classification. And I know that logistic regression, the name literally has the word regression in there, but it is for classification. All right. So we use logistic regression when the output is categorical, of course. And so how it works, like we said last time, if the linear regression predicts 0 or more, then the sigmoid will make it 0.5 or more. and then we predict the positive class. If it is 0 or less, then it's 0.5 or less, and then it's the negative class. That's for binary classification. And then we also learned last time that logistic regression is a linear decision boundary. Like, for example, here is all one class, these triangles and these circles are all another class. Logistic regression will try to find the best line. And when we go to higher dimensions, there'll be a hyperplane to separate, but it is a linear model. All right. The common evaluation metrics are what we discussed last time: accuracy, precision, recall, F1 score. And like last time, we also showed the confusion matrix, so you can also print that out using sklearn. Sklearn will do everything for you. Once again, the risk of overfitting is low. For high-dimensional data, use regularization for permitting the model to learn the data's random noise. Yeah. So here is the syntax. Again, it is linear model because, of course, the logistic regression, we showed the formula. It is linear regression, but just put a sigmoid on it. So it's a linear model. Import logistic regression, instantiate it. The parameters are all good. You don't need to specify anything here. Like the default parameters are all good. And then fit the model on the X train and Y train, and then predict. That's it. Evaluation, you can, from the metrics, again, from the metrics library under sklearn, you can get accuracy score, confusion matrix, F1 score, all of these. And then you just use these right here. You give the y-test, y-pred, y-test, y-pred, y-test, y-pred, and then you will get all of these important metrics. You can print them out. And once again, logistic regression, you can get the weights and the biases, the coefficient and the intercept. All right. Now let's talk about decision tree. Decision tree is a very different kind of machine learning model from logistic regression and linear regression. Decision tree does not use gradient descent to learn because it does not really have like traditional parameters. Instead, it looks at all features in the dataset and splits the data into two nodes based on a feature threshold. And the most common types of trees called binary tree, that's the two nodes. Of course, you can have more complicated like 3 nodes, whatever, but even most machine learning models are not like that. Then for these two nodes, each is split into more nodes, 2 smaller nodes, and the process continues. Okay, I will model a sample process for you in a little bit. Okay, the splitting process should give us the most information. So that is how, that is for linear regression, we're trying to learn which parameters are the best. And we try to minimize the loss function. But for here, there's not really loss function. Here, we're just trying to have the best split so that it gives us the most information. And what does that even mean? That means we want to try to make each split be more pure. So there's something called entropy. It measures the disorder of a node. And Gini score is also another similar. The formula is very similar to entropy. We don't need to go into the actual complex formula, but just understand that entropy is disorder of a node. And what do I mean by disorder? Well, let's say we have 10 samples, and 5 is class 0 and 5 is class 1. Then 0, 0, 0, 0, this 5 zeros split, and 1, 1, 1, 1, this split, this kind of split is the best possible, right? So this is very pure. So for this node is very pure, for this node is very pure, because it's just one class. However, okay, and by the way, this is a typo. This is a typo. This is supposed to say 0, 0, 0, 0 and 0, 1, 1, 1, 1, 1. So here we are splitting a 4 by, so here the node has 4 things, here the node has 6, that's fine. It does not always have to be like an equal split, that's fine. But here, even if we have like more things here, because there's a 0 here, the entropy cannot be the smallest possible, because there is some disorder here. Okay. However, this kind of split, you can see it is much better than this kind of split. You can see here, there's both 0s and 1s and both 0s and 1s, and it's all mixed. So mixed means high entropy. That is not good. We want lower and lower and lower and lower entropy. The feature threshold with the most entropy decrease wins, and the process is further propagated now. And I'll show you what that means. Okay, and then we'll talk about this figure. Okay, so let me go to here. Okay, so here's an example. Let's say we have this data set. So let's say we have a feature called color, we have a feature called height, and we have a feature called is this person happy? And the color is his favorite color. So let's say somebody is red, somebody's favorite color is blue, and then red, and then blue. And then the height is like 5.5 feet, 5.1 feet, 5.2 feet, and 5.4 feet. And this person is not happy, not happy, not happy, happy. So here is how we model what a decision tree would do. So right now we have everybody, and let's say this is 1, 2, 3, 4. This is the index of the people. So they're all here. Let's say the tree finds that the best like splitting threshold is height is greater than 5.3, and on this branch is height, of course, less than equal to 5.3. So then what do we have? Well, we can see that greater than 5.3 is 1 and 4, and then less or equal to 5.3 is 2 and 3, right? Well, 2 and 3, they're both already part of the 0 class. They're both not happy. So if you split more, it doesn't even matter, right? So this, we're done. But for this one, what's a good split? Well, they're already both more than 5.3, so what should we look at? We can look at color. So the color might be, we want the set. If it's just red, you go over here. If the color is blue, then you can go over here. And right now, I only use 2 colors. But if, let's say, there's red, blue, and green, then maybe on the left, it could be color is red or green, and on the right, it could be color is blue, something like that. So it's just subset of the categorical features. So notice that for numerical features, we define a threshold. For categorical features, we do subsets. Okay, well, the red person, the person whose favorite color is red is 1, person whose favorite color is 4. So this is good. So you can see here, right here, for this 1 and 4, 1 is not happy, but 4 is happy. So this, the entropy is not the lowest. But when I make it to be just 1 by itself and 4 by itself, then the entropy is decreased, and that is good. Okay, so some things to note, and you can write this down. I'm not gonna write this down because it's already in the notes here, but just listen to my summary, and you can write this down if you want. So first, the tree should, all trees you'll see in machine learning are binary. Second, so the algorithm is basically, we look at each node, we find the best feature to split, we find the best feature and the threshold to split on. And then we see, is that split, will that split actually decrease the overall entropy? If it does, then make the split. If it doesn't, then we stop. And when we stop, these are all called nodes, right? But the final nodes right here, there are no more splitting. It's called a leaf. It's called a leaf, or you can say leaf node. So for each node, let me reiterate. So for each node, we'll find the best feature and threshold to split. But if that split does not even decrease the overall entropy, then we should stop, and that's it. So when the tree is fully constructed, you can see here's my training data set. But when there's a new test sample, what do? Well, I'll just see, oh, is the test sample's height more than 5.3? Okay, it is. Then let's go over here. Is the color blue? Okay, it is. Then let's go over here. Then I end up with this leaf. So how do I predict the label? Well, for classification, you just predict the majority in each leaf. So for this one, there's like 0 and 0 here, right? So for any test sample that lands in this leaf, the output is just 0. For any that lands in this leaf, the output is 1. And for any that ends in this leaf, the output is 0. Okay. For regression, what we do is we just take the mean of the samples. So for this training sample, we'll just take the mean of these. It is a number, and then we just output that number. So for regression, you can see that many test samples, although they're different, we will just predict the same exact value because we're just giving them the mean of the trained samples that went to this leaf. So that's a little bit not like linear regression. Linear regression, if the test samples are different, um, when you multiply by the theta, it'll definitely be different. The Y prediction will definitely be different. But for trees, it will not. Okay. So here's like a real life example of a tree. And you can also output these kind of graphs in sklearn. So this is the famous iris data set. So here is the feature. You can see the threshold. We're saying less than or equal to 2.45. If that's true, then go over here. If that's false, then go over here. You can see the Gini scores right here. So look, this is 0.6667. Here, the Gini is 0. Here, the Gini is 0.5. Oh, well, I can clearly see that when I split, the Gini decreased. The total Gini decreased. That's great. You can see here, the split is insanely good. For this split, I got 50-0-0. That means everybody is of the Setosa class. Then I'm done. There's no more splitting needed to do. But for here, I have two classes. I have versicolor and I have virginica. So what should I do? Okay, let me find the best parameter to feature to split on is petal width. And then I have these two nodes. And then I continue to split. You can see here. And for each split, I'll try to decrease the Gini score, right? Okay. So decision scores can be used for both classification and regression. Yeah. The main hyperparameters are max depth. It's the limit on, like you can see here, here is like layer 1, layer 2, layer 3. So we set a limit on how many layers it can have. And there's another important one, which is min samples leaf, is the minimum number of samples on a leaf to split further. So for both of these, if you want to prevent overfitting, you can decrease the max depth and you can increase the min samples leaf. And let's just think about why that is. So if I have, like I let the tree just split infinitely, it'll definitely stop at some time, but it might just make a split in the end that's just based on like pure noise. And it does not even like represent the data well. So if I say decrease the maximum depth, that prevents overfitting. And for minimum leaf samples per leaf, you can also think about that on your own. We're kind of running out of time. Okay. Another hyperparameter is the criterion. You can use Gini or entropy. Yeah. So here is the syntax. The library is called tree under sklearn, and you can import classifier or regressor. And again, you can set your own max depth, fit the model, predict, etc. And here, you can learn how to plot one of these plots if you want.